I must say, over the years, I've heard consistently many things, many good things, only good things about this conference, and so it's a pleasure to eventually attend. I had not this chance when I was a young guy, unfortunately. Okay, so first I'd like to say that this is joint work with my colleague Thomas Verdeboe in Brussels, and most of the work I will actually present today is also joint work with our former PhD student Julien Rémy. So the title, as you can see, is Inference in PCA under weak identifiability. I must say that the topic is not so much PCA, so you all know about principal component analysis. The topic is really this weak identifiability component. And PCA is only one framework where such weak identifiability will materialize, but there are actually many other frameworks, I think, where it might materialize. And in our recent research, we considered other such framework. But again, PCA is the setup for today. So brief outline of the talk. I said inference, so it will cover, say, both hypothesis testing and point estimation. But as you can see, I will mainly focus on hypothesis testing. And within hypothesis testing, I won't comment further. This is, as you can see, rather a standard structure. So let me start with a cheap introduction. So I start with the following toy real data example that was covered by a book by Fleury in the late 80s. And this is a low-dimensional data example. You have 4 dimensions, and you see there the 4 variables that we consider. So these are all associated with Swiss banknotes. And you have there 4 variables, LRBT, and this stands for the width on the left and on the right-hand side of the banknotes, and the size of the bottom and top margins that you have with respect to the picture that is plotted on those banknotes. And actually, in this full data set, we have counterfeit bills and we have genuine bills. Here we restrict to counterfeit bills. And we can expect that on counterfeit bills, you have much more variability than on original bills. And to see where this variability actually materializes, it's natural to try and conduct a principal component analysis. So this is what Fleury did. Okay. So what he obtained are the following results. So I'm not showing the empirical covariance matrix, but I right away go to the eigenvalues, the lambda high hats that you see there, and the corresponding estimated eigen directions, the theta I hats that you see there. So unit eigenvectors, estimated unit eigenvectors. And so in particular, Fleury is, or you may look at the first, say, eigenvector, and what you see. So I think that variables are roughly the same scale, so that it makes sense to compare the magnitudes of the various entries in those eigenvectors. So what you see in this first eigenvector is that basically those components associated with ln and r, that they are quite small. And then you are left with something which is a contrast between B and T, between the upper and lower margins. So that means that a large value of the first principal component or a small value of the first principal component will be obtained when the image on the banknote it is above the banknote or more below the banknote, right? It's some kind of variability of the location of the image on the banknote, right? That's how you will obtain a large margin associated, a large top margin associated with a small bottom margin, and or vice versa. Okay, and so this is a clear interpretation, hopefully, of the first principal components. And of course, when you have interpreted the first principal component, you want to go to the second one. And now if you look at the second one, it's a bit the converse, that is now B and T are not playing a role. And what you have is not a contrast, but is some kind of aggregate of the other two variables, L and R. So that will take, so the corresponding second principal component will take a large values or a small values when the banknote is tall or is not so tall, right? This is the kind of the second source of variability. So this is also a rather neat interpretation. However, Fleury writes something which might be puzzling at first. Fleury writes, beware, the second and third roots, so read the second and third eigenvalues of the covariance matrix, they are quite close to each other. These are these 13 and 10 above, which indeed, relative to the full scale of the spectrum, may be considered quite close, opposed to these very large eigenvalues and to this very small, smallest eigenvalue. And he writes something like, and because of that, the computation of standard errors for the coefficients of the corresponding eigendirections, well, this computation may be hazardous. So this may seem a bit mysterious. And what this hides is the following. So if you open a book about multivariate statistics, classical books such as the Anderson book on multivariate statistics, you will find that the asymptotic, the theta 2 hat, the second principal eigenvector, as a well-known asymptotic distribution, it's root n consistent, it's asymptotically normal, I would say, as usual. But then you have the covariance matrix that you see in the middle of the slide there. And what you can see there is this red factor. If we have an eigenvalue lambda L, which will be close to lambda 2, which is exactly what we have in our setup, in this case it was lambda 3, well, if lambda 3 is close to lambda 2, you will divide by something which is close to 0. Right? Meaning that this asymptotic covariance matrix, it will be very large then. And when a covariance matrix is large, you get confidence zones or you get confidence intervals for marginals of the object you want to consider confidence intervals for that are very wide, that are very large. And so in the end, you are not confident that the value you got for your estimate is precise, reliable, can be trusted, whatever, right? So because we are in a concept, in a context where this lambda 3 is close to lambda 2, lambda 3 hat is close to lambda 2 hat, we cannot trust that indeed the true theta 2 that we are estimating is close to that, right? And that's why Fleury warns the reader about making a clear interpretation about this theta 2. Okay, so this provides a motivation to study what can be said about this theta 2, not in a classical framework where lambda 2 and lambda 3, they would be far away from each other, but in what I will call a weak identified, I will make this clear later on why I use this name, why I use this terminology, but in a weakly identified framework where lambda 2 and lambda 3, they are close to each other. Okay, this is a bit the motivation for what we are about to do. Okay, now we can enter the theoretical framework. And, well, of course, nothing is special about theta 2. So to fix idea, we'll consider theta 1. And I will assume that the corresponding eigenvalue lambda 1, it is close to the next eigenvalue lambda 2. Okay, of course, eigenvalues are ordered as usual in a decreasing way. So lambda 1 is the largest one and lambda 2 is the second largest one and so on. So this is the framework that I will consider. In some sense, you cannot dream of anything simpler. That is, in this modern high-dimensional statistics literature, where the dimension might, increase with the sample size, and no, the dimension will be fixed forever. and it will be fixed to P. And unlike as in non-parametric statistics, where we would have, non-Gaussian distributions or heavy tail distributions or whatever, no, we will stick to a Gaussian framework. Okay, so you might get rid of that, but I guess that if you restrict to such a canonical somehow framework, to such a standard framework, and if you still have the crazy things that I'm about to show, hopefully, then this is very striking that these materialize in a framework that we would all consider as pretty much standard. So what is non-standard? What is non-standard is that I will work with, or not so standard, is that I will work with triangular arrays of observations. So that is just not x1, xn, but you have double indices for those observations. So at each time n, say, I start from scratch and I sample again a new IID observations. And the reason why I do that, why actually I need to do that, is that those observations, they are sampled from a distribution that will actually itself depend on n. So I have a Gaussian with fixed dimension, okay, but I have a mean mu that might depend on n. This will actually play no role in the sequel, but most importantly, I have a covariance matrix sigma that might depend on n, and it will depend on n. So again, un does not play any role, but sigma n will be the star here. So what do I enforce as a structure for sigma n? Again, to have hopefully striking results, I will go to a very simple structure. And the simplest structure that you can think of when you want to make inference on θ1, which is again be the eigenvector associated with the largest eigenvalue, well, it's a framework where you have, of course, a largest single eigenvalue, but where on the contrary, all remaining eigenvalues, lambda 2, lambda 3, up to lambda p, they will be equal to each other, okay? And this is exactly what we have here. So you see you have lambda 2, lambda 3, lambda p that are equal to each other. But then you have a lambda 1 that is different, and that is actually strictly larger, right? Sigma square n is an overall scale factor that will not play a key role again. What will play a key role is this Rnv that makes the difference between the largest eigenvalue and the subsequent equal eigenvalues. So this Rn, I take it as a positive number, and also V now as a fixed positive number, so that indeed lambda 1 is larger, really strictly larger than the remaining ones. So because it's larger, this lambda 1, I have a single well-identified corresponding eigenvector θ1 in principle, right? Whereas the remaining ones, θ2, θ3, θp, they are not well identified because you have a p-1 dimensional plane of eigenvectors, right? And now, since θ1 is well identified, I can perform inference on θ1 in principle, and I can consider here the hypothesis testing problem that you see there. So I just fix a vector θ1, 0. I fix a vector, a unit vector in Rp, and I wonder whether indeed the true value of θ1 is this very vector. So if I come back to my motivating example, where am I? I'm over there. And this θ2 that I'm here, I'm tempting to take for θ2, 0, something which would be 1, 1, 0, 0, and then I divide by the factor that I need to get a unit vector. So this would say, okay, I think that indeed this θ2 is a perfect aggregate of the first two random variables. Okay, so this is the type of testing problem that I consider. Okay, and now you have two different setups. You have the setup, which is the classical setup, where this Rn, that I will read in the sequel as a rate, this Rn is fixed, say to 1. And then this lambda 1n, divided by lambda 2n will be a fixed quantity. Lambda 1n divided by lambda 2n will be a fixed quantity, right? It will be 1 plus v. Okay. So the lambda 1n will not get closer to lambda 2n. This is what I mean. Okay. But actually, the framework we are primarily interested in here is the framework where Rn goes to 0 as n goes to infinity. A framework in which lambda 1n divided by lambda 2n will go to 1. And so in this framework, indeed, you will have the first eigenvalue that gets now arbitrarily close to the second eigenvalue, which is actually what we were observing in the real data example. Lambda 1 is close to lambda 2. And I claim that this is a challenging setup because it's a setup that I want to call weakly identifiable. What do I mean with that? Well, in the limit, that is as n goes to infinity, at the end of the movie, lambda 1 divided by lambda 2 is 1. All eigenvalues are equal to each other. And so theta 1, the eigenvector I want to make inference on, it is not identifiable anymore, right? If you have a spherical distribution, if you have a soccer ball, you have no particular eigenvector theta 1, right? And this is in contrast with what you have in our model there. When you don't have a soccer ball, you have a rugby ball. And in rugby ball, you have this theta 1 that is special. Okay. So since at the end of the movie, this theta 1 is not identifiable anymore, you can guess that it will be challenging for large n to make inference on this theta 1. And so we wonder, what can we say about this theta 1? Okay, so to explore that, I will focus on 2 tests. And I've been very slow, so I won't say much about those 2 tests. But let's say these are 2 classical tests. And in particular, the first test is what you will also again find in the Anderson's book. This is just a Gaussian likelihood ratio test for this considered model. Whereas the second one is a Rao score test. So there are 2 different ways, as we know, to build reasonable tests of hypothesis. And you see there the corresponding test statistics and under the null hypothesis in the usual framework where the eigenvalues will stay separate from each other. Those 2 test statistics, they are asymptotic chi-square p minus 1, and you reject for large values, and that's why you see that the critical values there is the alpha upper quantile of the chi-square p minus 1 distribution. Okay. Maybe I just say a word on the interpretation. So here you see that you have an inner product between the estimate for theta j and the value you test for theta 1. So of course this will estimate the true inner product between this thing. And of course, if theta 1 coincides with theta 1, 0, where then this inner product should be the inner product between mutually orthogonal eigenvectors. So this inner product should be 0, right? So you expect this quantity in the box there, the blue box there, to be close to 0, right? So you expect its square to be small. So that's why we expect this full test statistics Q and R to be small under the null hypothesis. And so we should reject for large values of this test statistic, which is exactly what this test is doing. How large? Larger than this critical value based on the chi-square null asymptotic distribution. Okay, so this is the idea. I don't want to say much more. These are 2, I think, natural test statistics. But what I want to say is that in the classical framework where eigenvalues remain fixed forever, they don't depend on n again, those 2 test statistics, they are perfectly equivalent under the null. So in mathematical terms, the second one, say, is equal to the first one plus something that will converge to 0 in probability, right? So under the null, they're perfect. They behave in the exact same way, and also under local alternatives that will be contiguous to the null hypothesis. They will also show the same power. So in every standard textbook, one would really consider those two tests as equivalent asymptotically. Okay. But now, of course, our purpose is to consider this challenging framework where the eigenvalues they get close to each other. Okay. So first result is the following. So first of all, mu n and sigma n, they are only there to make things artificially complicated, but they don't play any role. And the reason for that is that those two test statistics that we consider, their behavior does not depend on mu n and does not depend on sigma n. So in particular, those two test statistics, they will be invariant when you translate the data set by a constant vector, because they are a function of the empirical covariance matrix. And so this ensures that mu n does not play any role. And similarly, you can show that sigma n does not play any role. So first result is the following. If you consider the score test, so not the likelihood ratio test, but the score test statistic, well, the score test statistic under the null hypothesis, and you see the null hypothesis there because I enforce the true eigenvector to be the θ1, 0 I'm testing for. It remains chi-square p minus 1, which is the asymptotic null distribution that I was claiming be the true one in the standard setup obtained with Rn is equal to 1, standard setup where the eigenvalues remain well separated. But actually now it will remain this distribution as soon as Rn is any bounded sequence. And in particular, Rn might be a sequence that converges to 0, which is our challenging case. So what we learn from this result is that under the null, in terms then of null size, of level, if you wish, this particular test, the score test, will not be affected by this strange, weak identified framework. And this is something that we can check by simulations. So what we did here was to consider the scatter matrix, the covariance matrix that you have up there top right. And you see that indeed, the next eigenvalues, the smallest eigenvalues are 1, and the largest eigenvalue, it's close to 1. And the larger L, you see that L gets larger if you go there. The larger L, the closer the first eigenvalues to the next ones. Okay, and so the more severe this weak identifiability thing. And what you see there are null rejection frequencies, so rejection frequencies under the null hypothesis for a moderate sample size and for a crazily large sample size. And you see what you expect. That is that if you perform the test at level 5%, you basically have 5% rejection frequency everywhere. And so your test behaves as well under this complicated framework that on the left of the picture under the standard framework, right? So you might say, why all this first then? Well, all this first because if you look now at the other test, and if you record the corresponding null rejection frequencies for this other test, the likelihood ratio test, beloved likelihood ratio test, basically you die. That is, although you are still recording null rejection frequencies, so rejection frequencies under H0, and you are supposed to reject the null hypothesis in 5% of the cases, now you start rejecting the null in 90% of the cases, or 95%. It looks like a great power, not like a reasonable size on the null, right? So this is completely crazy, and you will say, okay, this is just maybe a small, it's not good, of course, but maybe this is a small sample phenomenon. And maybe now when I will go from 200 to this huge sample size. Now this will be corrected, right? So you perform the simulation again and you get this. So something is going on. And I think you don't even need a theorem now. It's clear that this likelihood ratio test is not robust to this weak identifiability thing, right? If the lambda 1 is close enough to the lambda 2, the test does not behave well anymore in terms of level. But if it's far enough, it seems that it's still okay. Right now, you are close to 5%. So this is what those rejection frequencies suggest. If lambda 1 converges to lambda 2, but not too fast, which is this case, maybe you keep the same chi-square distribution. But if lambda 2 and lambda 1, they converge to each other too fast, and then this chi-square p minus 1 distribution will disappear, and you pay a price. And this is exactly what the next result says. So now we consider QLR. Now we consider the likelihood ratio test statistic. And as you can see, in the usual setup where Rn is fixed, or in a framework where Rn would go to 0, but not too fast, not faster than 1 divided by root n, or not as fast as 1 divided by root n, okay, you keep the chi-square distribution, the p minus 1, chi-square p minus 1 distribution. So you will reach the target level. And I don't want to show this complicated distribution that we were able to identify in the remaining cases, but what I want to make clear is that it's not the chi-square p minus 1 distribution anymore, okay? And in particular, in the framework where Rn would go to 0 faster than this 1 divided by root n, in dimension 2, it is a funny thing, what you get is 4 times a chi-square p minus 1 distribution. So in the standard setup, you have a chi-square p minus 1. And now in this non-standard setup, you get a 4 times chi-square p minus 1. And this 4 kind of comes from nowhere. And you can, again, show that through simulations. So these are histograms, again, computed from values that you generated under the null for your test statistic. Now the likelihood ratio test statistic under various framework where lambda 1 and lambda 2 they are close or not so close to each other. And what you see, if you are in the standard setup, or if you have in a non-standard setup, but in a non-standard setup where lambda 1 and lambda 2, they don't get too fast close to each other, you see that the distribution is well fitted by chi-square 1. Chi-square 1, of course, is chi-square p minus 1 in dimension p is equal to 2. Whereas if it's now too fast, that those lambda 1 and lambda 2, they get to each other. Now it's the blue curve, which is associated with a 4 times chi-square p minus 1 that provides the true distribution. Okay, so very strange thing. And you see the corresponding null size that are really blowing up again. You are supposed to perform the test at 5%, and you reject in 32% of the cases. Okay. And now I want to say something about what occurs under the alternative. So what we show is that we have 2 tests. Those 2 tests, they are in standard textbooks considered equivalent. But now this equivalence, it blew up, right? I mean, one test remains valid under the null, under weak identifiability, and the other one, it collapsed miserably. So now we can then forget about the likelihood ratio test. It died, right? It does not make any sense to look at its power. It's not even a valid test. But it still makes sense to look at the power, at the non-null behavior of the score test, right? Because that one is robust to this weak identifiability thing. Of course, it's not difficult to define a robust test. You just flip a coin, right? If you flip a coin, you can get exact null size alpha, and this would be robust to any pathological feature you can dream of in the data. But of course, this will not be robust in terms of power. Flipping a coin will not bring any non-trivial power. So there is a hope that this score test, it still brings some power even under weak identification. So is this the case? Well, we have a first result that says, okay, in the standard framework, but also in the non-standard framework, but where lambda 1 and lambda 2, they get to each other, they get close to each other, but not too fast. Well, in this framework, the central chi-square distribution that we add under the null transforms under the alternative to a non-central chi-square distribution. Of course, this non-centrality parameter is what will bring the power, right? But actually, what you see, so from there, of course, you could compute the corresponding local asymptotic powers. What you see is that to get this asymptotic non-null distribution, you need to consider local alternatives that will depend on the amount of weak identifiability. So it's a bit the same as in the standard framework, right? If you consider in the very standard framework where eigenvalues will stay separate forever, if you consider a fixed alternative, then the power will go to 1, right? This is just consistency of the test. And to get a non-trivial limiting power, you will need to consider more and more challenging alternatives that shrink to the null hypothesis, right? Well, what this result shows is that those shrinking alternatives, under which you will get this non-trivial power, they are at a rate root n if you are under the standard framework, where eigenvalues, they remain separate forever. This is the case, so Rn is equal to 1. But if Rn goes to 0 goes to 0, so that you bring this weak identifiability issue, well, now you see that those local alternatives, they are more severe. They are further away from the null hypothesis. Huh? Meaning what? Meaning that, and this was our intuition, it's more challenging, it's more difficult as an inference problem to make inference on theta 1 under weak identifiability than under the classical regime, right? And this materializes in the fact that if you want to see something in terms of non-trivial limiting power, you need to go further away from the null hypothesis under weak identifiability than what you needed to do under the classical framework. So what about the other three regimes where eigenvalues are closer to each other? Well, if they get close to each other really fast, faster than this 1 divided by root n rate, then this chi-square, this central chi-square p minus 1 distribution that we had under the null will remain the central chi-square p minus 1 under the alternative, right? That means, well, no power then, right? I mean, if the asymptotic distribution is the same under the alternative and under the null, that means no power. So power alpha, power that will coincide with the nominal level. Or you might say, okay, no problem. If you don't see those alternatives, just look at more severe alternatives until you will be able to see those alternatives, right? However, this is something we cannot do here. You cannot look at alternatives that are more severe than the ones that I consider there. And the reason is that theta 1, our parameter of interest, it's a direction. We are looking at principal directions. So it's a unit vector. And the sample space, say it's not the sample space, but the parametric space for an eigenvector, for a unit eigenvector is the unit sphere. And so I cannot say consider a more severe alternative, such as, for instance, this one, because of course this would let me go outside the unit sphere. I'm stuck to the unit sphere. So this alternative that you see there in red is the most severe one that I may consider. And if I don't see this one with this test, that means that I cannot see any alternative with the corresponding test. Okay. Of course, it's bad news. It means if lambda 1 is so close to lambda 2 that my score test that was robust to weak identifiability does not show any power. And then in the intermediate framework where you exactly go to 0 as fast as 1 divided by root 10, you have actually a non-standard non-centrality parameter. But for the sake of time, I won't comment much further on that. So, but you still see something. You get some power, and actually you get some power under those most severe alternatives that we would be allowed to consider. So the section is entitled null. Is entitled non-null behavior under local alternatives. But actually, there were quotation marks for this local thing, and indeed these are actually non-local alternatives, since those local alternatives that you have in this part 3, they don't shrink to the null hypothesis, right? They are kind of fixed. I still want somehow to call them local, because these are alternatives under which the test will not be consistent, right? The limiting non-null rejection probability, so the limiting power will not be 1; it will be a non-trivial power. Okay, what about optimality? So we should be happy and not happy maybe at the same time with this score test, because it shows some power under some alternatives. But of course, you have no clue whether there is not a third test that will also be robust to weak identifiability, and that might show now higher power than these score tests. Maybe even a test might show some power under more challenging alternatives, under less severe alternatives. And maybe you can be clever enough to identify a test that will show some power in this case where the score test was not able to show any power. Of course, to answer such questions, you should not look at a particular test, right? You should look at the model itself. You should look at the statistical experiments themselves in the terminology that is used in this LeCam theory, because this is indeed what we used. So without entering too much into detail here, you can actually, at the model level, investigate the structure of such local locute ratio. So this is the log of something that makes sense that it makes sense to call a likelihood ratio. So you have in the numerator there the distribution under an alternative, and you have in the denominator you see there the null hypothesis. You have the null value θ1 0. So null value θ1 0 is just over there, and then you see you perturb it appropriately in a hopefully local way again in the numerator. And of course, typically you want to base inference on this on such an object, right? This is what we do in our beloved Niemann-Pearson fundamental lemma, right? We reject when this likelihood ratio equivalent its log is large. Now, in a local framework where typically the new n that is there would go to 0, it makes sense to expect that such a local likelihood ratio allows for a nice expansion, Taylor expansion. But no, of course, a Taylor expansion, that would be a stochastic one. That is, since I'm facing random variables, the remainder term will itself be a stochastic component. And actually, you can show that in the frameworks that we were considering, or at least in those regimes 1 and 2 that we have considered, so the classical one and the not so classical one, you get such a second order expansion. And if you look at what you have when you don't look at the remainder term, what you have is actually a very standard expression, and this is actually the exact expression you would get for such a log likelihood ratio in a very simple experiment where you would observe a single observation delta n that would be Gaussian with a mean that would be gamma tau and with a variance that would be gamma. Gamma with a specified thing, and the parameter would be the tau of the tau n that you have there. So it's a very simple model because it's Gaussian. It's just one observation, and it's a Gaussian model because the parameter is tau. You see that there indeed the parameter of interest basically is tau. And this is about tau that you would like to learn something. Is tau equal to 0 and then I'm under the null? Or is tau different from 0 and then I'm under the alternative? So long story short, what this result says is that basically the log-like ratio in my complicated PCA weakly identified model as n goes to infinity, and if I look at local alternatives, it now behaves asymptotically exactly as this single observation delta n in a very simple model. So, and in such a framework, actually, I might simply design the optimal test in the limiting Gaussian model and then substitute for this single observation delta n what plays the role of delta n in the above stochastic expansion result. And this Lecam theory just ensures that in a very strong sense, if you perform this agenda, then you end up with a test that may be considered optimal. Asymptotically, of course, because n needs to go to infinity to have this equivalence above, but also locally, because I needed to restrict to local alternatives. The funny thing is that if indeed you write down what is this optimal test statistic in this limiting Gaussian model, which is basically something like a Noetherling test, right? A quadratic form in your single observation delta n. Well, you can easily show that actually, as the sample size n diverges to infinity, you get something that under the null is asymptotically equivalent to the score test. So if the left-hand side is an optimal test statistic, well, then the right-hand side, the score test, is also an optimal test statistic. So what you learn from this is that there is no way in this regime 1 and this regime 2 to end up with a test. And you may be very clever. There is no way to come up with a test that will improve on the performance of the score test that we had investigated before. Okay. And this is the story. And you also learn that this rate that we looked at when deriving the asymptotic powers of the score test, this rate is optimal. That is, if we consider whatever rate that would converge to zero faster than this thing, there is no test out there that will be able to see those alternatives with a non-trivial power. So in these regimes 1 and 2, the score test is optimal in terms of rate, and at this rate also in terms of limiting power. And so, of course, the question is, what about those even less standard regimes, 3 and 4, where the eigenvalues, lambda 1 and lambda 2, they converge to each other even faster? Well, in regime 4, which is the worst case, where they would converge to each other even faster than 1 divided by root n, well, you can show that even if you take what I called before the most severe alternatives that you may consider in this framework, even for these most severe alternatives, the log likelihood ratio goes to 0 in probability. So then the likelihood ratio itself goes to 1 in probability. That is, there is no way to discriminate between the distribution in the numerator and the distribution in the denominator in this likelihood ratio. That is, not only the score test will not be able to discriminate between the null and the alternatives here, but no test at all can discriminate between the null and the alternative. So what we read as a bad news for the score test in this case 4, well, okay, of course it's a bad news, but there is never any hope to get good news in this framework. So if I want to sell this score test in this case 4, I may just say, and I would be right, the score test in this case 4 is optimal, right? I mean, it sucks, but all tests will suck. And in the sense, it does as good as it can do, right? So it's optimal. And again, the story in this case 3, which is clearly the complicated framework, is more complicated. And there, you don't have this nice Gaussian model that you have the limit, which is a so-called LAN structure, which is a so-called locally and asymptotically normal structure. You have a more complicated limiting model where even at the test statistic level, even at the first order level, you would have something which is not linear in tau as before, but something which is quadratic in tau. And this is really non-standard framework. And in this non-standard framework, we are not clever enough to identify the optimal test even in the limiting experiment. So in this original model, then also we are not able to say what is the optimal test. But of course, it's tempting to look at what happens for small tau. That is when you deviate just a little bit from the null hypothesis, not in terms of rate, nu n, but also in terms of tau. And then, of course, if you do that, well, if you do that, you can really neglect, of course, this tau n compared to what you have there, the theta 1, 0, that is fixed quantity if 2n is small. And of course, you can also neglect this power 4 of this small quantity compared to the power of 2 that you have in the next term, in the previous term. And if I do this now, I'm back, say, to an exact LAN thing again, a standard limiting Gaussian experiment, where I can claim that the corresponding test will be optimal. And if you do that, then you get QS again. You get the score test again. So the score test in this complicated regime 3 will not be optimal for any tau, but it will be optimal if you just locally optimal, I would say, if you don't deviate much from the null hypothesis. So it's set there for small tau. But I mean, a corollary of this result is that the rate, which was not so favorable, the rate of the alternatives we were able to detect, which is a very poor rate, because this is the rate that will provide fixed alternatives. Well, this rate is also the optimal rate. So again, now if I would look at any genuine local alternatives, a sequence of alternatives that would shrink to the null, well, no test would be able to detect the null hypothesis, would be able to detect the alternative in this framework. Okay, so I see that I've been speaking for 50 minutes already. So let me quickly go through a couple of slides to just summarize the message for the next points. If I may, Alexandre. Yeah, thank you. So very quickly then. Maybe just one word about the real data example. So about the real data example, again, indeed, this is the natural thing to test for. So you want to test, as I explained before, that the theta 2 is an aggregate between L and B, between L and R, the L and R that you see there. And if you perform the two tests that we looked at, well, you see that the score test, it will not, at the usual levels, lead to rejection of the null, so that you can indeed then interpret theta 2 in the way Fleury would have been tempted at first to interpret it. But the likelihood ratio test, it sounds suspicious, right? but let me pretend that I want to perform this testing problem at level 10%. Well, then it would reject the null hypothesis, right? This is as if we would have cheated, right, with the data there. But I can provide the data. It's really the p-value that we get. So in any case, it would quicker reject the null hypothesis than the other test. And since we learned from the theoretical analysis that this likelihood ratio test has, in any case, a strong tendency to over reject the null hypothesis under weak identifiability, here we are confident that the correct decision, say, is not to reject the null hypothesis. Okay, so this was for the real data example. And now just a word to say that I stick to the Gaussian to hopefully have striking results, but actually this is not at all related to the Gaussian distribution that happens there. And in particular, what we did is to extend this to arbitrary elliptical distributions with finite force movements. And basically what you show is exactly, you need to correct for the underlying kurtosis, right? But you get the exact same phenomenon in terms of robustness to weak identifiability, both under the null and under the alternative. So long story short, the weight of the tails do not have an impact on the results. We can go for heavy-tailed T distribution. We'll have the same creative things as we have seen before. And one test, the green test, the score test, will remain robust to weak identifiability, whereas the robustification of the likelihood ratio test will again collapse. If you want to go for even heavier tails, then you can define tests that are robust tests. And of course, now you should not go for Gaussian type tests, but you can go, for instance, for tests that will be sign tests or something like that. And you have again the same type of phenomenon. So just a word about now point estimation. So maybe you just want to estimate θ1. Right? So how do these results translate if you want to estimate θ1? And then I just maybe show this slide. So in the standard setup, you get the basically the result I was describing before. So your estimate for θ1 would be it's not the θ1 hat based on the sample covariance matrix, but it's the θ1 hat that would be based on a robust estimator of the covariance matrix. But what you get is the same type of phenomena. That is, you have root inconsistency and a rather standard asymptotic normal distribution. So this is in the standard framework where the eigenvalues will remain well separated. And then, of course, as before, in the subsequent frameworks where eigenvalues will get closer, well, you see that at first you keep an asymptotically normal distribution, but what you lose is the consistency rate. You have a consistency rate that will be poorer. Rn goes to 0. So the consistency rate will then be poorer than in the classical fixed case. This is what we expect because, again, it's more challenging to make inference about θ1 in this case. But if it goes too fast to 0, is Rn, then in the end you lose it all. And this is, I think, a very good way to say that you lose it all. That is, your estimate for θ1 will be a direction that is completely random on the sphere. That is, you can show that the exact asymptotic distribution is the uniform on the sphere. So it does not bear any information at all anymore about θ1, right? So θ1 for any n is well identified, but if you look at the corresponding asymptotic distribution of its estimate, you have lost it all because you get a random direction. Whereas in the intermediate case 3 that you have there, you lost almost it all. You lost consistency, so it will not help that n diverges to infinity when you want to estimate it, which is, of course, not so good. But at least in this asymptotic non-degenerate distribution, you get something that will still depend on the true θ1. So it's a kind of threshold, this one divided by root and rate, between a setup where you can consistently recover the θ1 you're estimating, and a setup where there is no point, there is no hope to say anything useful about the theta one you are estimating. And now my time is really over, so I apologize for the extra time that I took, and I thank you very much for your attention.
Thank you very much, Davy, for this very interesting talk.
Thank you.
So I open the floor to questions. So if you have any question, I think the easiest is that you raise your hand on Zoom, but you can also just unmute if you like and speak. So I don't see any questions for the moment. So I have a few questions myself. I see the channel, but I'm going to ask one question and then give the word to Zikicha.
I see there is a question. Yeah, I see.
Yeah. But I'm going to ask mine first, and then yeah. So I see the theory, but do you have an intuitive explanation why the likelihood ratio tests fail so badly under the null? I mean, based on the form of the test statistics, for example.
I would say 0, and this, I mean, under the null. So that all tests eventually fail under the alternative. We agree that it's related to this lack of compatibility, that the fact that the problem is too challenging in the end.
Yeah, sure.
This, I think, is really intuitive, but the various behaviors that we get under the null, for this we don't have any explanation, and I think it's it's kind of mentioned there. So a natural question directly in line with what you say, Alexandre, is okay, this is the result for PCA. What if I know to another, and there are to other models where you also have weak identifiability? Will it be so that the likelihood ratio test will again be the bad guy? And will it be so that the score test will again be robust? We have 2 or 3 problems with it's a bit this message, but so maybe there is a meta theorem there in the line of what you say, that says okay, likelihood ratio and weak identifiability, they are not good friends. Why they don't like each other? Honest answer is I have no clue at the moment.
Okay, thank you. Zikicha, you had a question?
Yes, first of all, thank you for the great talk. It was quite amazing. My question is kind of philosophical in a way. So you said we are going to work in a Gaussian setting, and that assumption is going to be valid throughout the talk. Do you have perhaps any intuition what happens when we go outside of that setting?
So outside of the Gaussian
yes.
framework, we have formal results for that, and so Gaussianity plays no role. It's as simple as that. So the exact same phenomenons materialize under heavier tails than normal, under lighter than normal tails, in some problem under asymmetry. So all these I mean, standard properties of the Gaussian are not responsible for what is going there. So again, it was just a restriction to hopefully make the result more striking, but Gaussianity plays no role. Thank you for the question.
Thank you for the answer.
Are there any other questions? I have still one myself, but I'm giving the word to anyone if he or she wishes. I don't see any raised hands. So as I see in your last slide, I was wondering how hard it would be to go high dimensional, because I cheated a little bit because I see some of your slides in advance. And as I see, the problem gets worse and worse as you increase P, as you increase the number of variables. So do we have any leads on that? On any?
Yeah, that's fully correct. You saw it well. So indeed, so yeah, for any fixed dimension, the amount of over rejection increases with the dimension. Now, we tried a bit to look at the high-dimensional framework. I mean, from a theoretical perspective, of course, it's really difficult. It's really difficult for various reasons. And of course, one of the main reasons we understand it well, that is, you know, in high dimensions, when you have, for instance, the dimension p, now pn, that increases linearly with the sample size n. Now, you know, we have those what's the name for that? Phase transition phenomenon, where we are not able to consistently estimate the eigenvalues themselves, right? So even in a framework where you would keep, where you would stay away from this weak identifiability, even there, you are not able to estimate consistently the eigenvalue. So you can, as you can guess, when you add to that the weak identifiability component, it becomes a bit of a mess. But maybe the reason why we are not able to do it is that we are very, very bad in random access theory. So maybe we should invest 5 years in learning that. Thank you for the question. Of course, very valid point. And in this PCA context, this would make much sense, right? Because PCA is not used in dimension 4, in dimension 5. I mean, PCA is primarily a dimensional reduction method. So of course, you are fully right to raise this point. Thank you.
I see Andrea has a question.
Thank you. Yes, thank you for the lecture. Like Shikita said, it was brilliant. But as you just mentioned, random matrix theory, which is, I would say, probably the essence of analyzing PCA, and as we had last presentation exactly on the topic, how to study such cases. You analyzed it for elliptical distributions. Is it possible to extend it to more general random matrix cases? If there would be any other type of distribution for the included elements in the PCA, how to study it, say, in the asymptotic sense? Would this make sense, and could weak identifiability matter also for this? Just ahead of your lecture, we had a lecture on Wigner matrices and central limit theorems. For this.
Yeah, so the honest answer is that, of course, when we gave it a try, we gave it a try even in the most standard setup that you can dream of. That is in a setup where you would have a Gaussian distribution, and where you would have a single spike. So, you know, I mentioned the spike is theta 1. You just have one single favor direction, and in the orthogonal complement to that, everything is perfectly symmetric and everything is perfectly exchangeable. And I mean, I tend to think that if you are not able to solve or to say something interesting in this in this particular framework, then I mean, you tend to be reluctant to consider other models of, I don't know, matrices that would have ID entries, or you know, all these standard or at this current model in a frequent model in random access theory. So no, for us it was a bit of a you know, of a no-go there.
Okay, thank you. Thank you for your plan.
But I would be happy that someone, you know, pick the problem and say something in high dimension. I would be very interested in see the form that this would take in this framework. Of course, another thing that makes it difficult is that it's going from double asymptotic theory to triple asymptotic theory. So I mean, you know, you have n that goes to infinity, and then you have pn that goes to infinity, and then we still need this rn that lives its own life, right? This thing that controls how far are the various eigenvalues from each other. This still needs to be there. So triple asymptotics, I mean, yeah, one paper about triple asymptotic, but not 25. I mean, usually these are difficult problems.
I think you're just touching the issues of asymptotics in these frameworks that we discussed. Thank you. It's a great finish also for the meeting. Thank you.
Thank you. Thank you for your comment.
Are there any other questions? If not, I suggest we thank again Davy for this very pedagogical, very lively and interesting talk. I really felt like I had the impression of getting into the theory, which looks very complicated, but you made it look understandable. So thank you very much for this.
Thank you very much.